it's not like you're really jumping over it. Let's go up here and look. Let's take a look at these two dichlorocyclopentanes. Again, if we look at this carbon here, again, I always look at these. I make a decision because I know I'm going to come back and look at this chart. I always make a decision: is it the standard dash and wedge, or is it the reverse? And for standard dash and wedge, number 4 has to be going away from my eye. So I'm going to go ahead and prioritize here. Again, obviously, the hydrogen is going to be number 4. Chlorine beats carbon on both sides, so it's coming out. So that's going to be number 1. And then I have to make a decision on this carbon and then this carbon up here. Okay, so if you look up here, you've got a carbon with 2 hydrogens. You got a carbon here, you got a hydrogen and a chlorine on this carbon over here. So essentially, this bond here takes priority over this one over here. So chlorine was number 1, beats carbon in both directions. You have to make a decision on 2 and 3. This one's going to be 2, this one's going to be 3, because this one has 2 hydrogens, this only has 1, and it also has a chlorine. So you sort of see the logic you go through to prioritize these. Okay, then you have to make a decision. We're going 1, 2, 3 in this direction. Again, we're going in this direction here, so we're going in a counterclockwise direction. So that's going to be the S. It's going to be the S chiral center. This one happens to have 2 chiral centers. Okay, let's go over here and do the same thing. This is what I call the reverse dash and wedge. So what I mean by reverse is number 4 is coming out of the plane of the board. Now you can redraw this. You can redraw this, so you essentially you take 4, go back behind, have this chlorine coming out, but you also have to redraw this side over here as well. So if you use this reverse dash and wedge, then you don't have to redraw anything. In my experience, we've tried this over the years, redrawing them and things like that. Even when I redraw them myself, I always make mistakes. I have to look back and make sure, is that right or not? Is that exactly the same structure? So this one, Wade talks about this in the book. I really like this, and again, it's something that when I'm looking at chiral compounds that I work on in my research, or when I worked on when I was in industry, that's how we did it. We didn't try to redraw them, because we knew by redrawing them we'd make mistakes. So that's why we use that. So what I mean by reverse is number 4 is coming out of the plane of the board, not going away. So it's just the opposite. And so these, whether it's counterclockwise or clockwise, changes. Okay, it's the reverse. So in this case, okay, number 4 is coming out, number 1 is going away. Same decision here on this carbon and this carbon here that we made on this one over here. So it's the same prioritization. The one that has the chlorine attached is going to get a higher number because chlorine's got a higher atomic number than hydrogen or than carbon, okay, or hydrogen. So this one's going to get a higher priority. This is going to be number 2. This is going to be number 3. And so we're going 1, 2, 3 in this direction. But remember, number 4 is coming out, so it's not like we're really jumping over it in that case. But we're going in this direction, so it's a clockwise, but it's the reverse system. Okay, it's the reverse system. Reverse dash and wedge, we're going to clockwise, so that's going to be the S. Yeah.
If the carbon's attached to more carbons, it takes the precedence over everything, though?
No, not necessarily. Not necessarily.
The atomic number is how
You look for the atomic numbers of what's attached. I mean, you could have other carbons attached, but let's say you have fluorine or nitrogen or whatever atom, but you want to look for that prioritized based on atomic number. Carbon doesn't take priority over, say, nitrogen or fluorine or something like that. Okay? Yeah.
So if that was in the cis conformation, it would have 1 S and 1 R.
That's right. Well, this one has, both of these are S. So you would, how I take an arrow and I point at that position. What is the stereochemistry at that position? I point at this one. What's the stereochemistry at that position? Okay? Is it R or S? Okay? Sometimes you see it where people will number them. They'll give you the numbering on some exams, but most of the time they're going to tell you if you have 2 chiral centers, they're gonna actually literally point to them, so you know which one to do. But sometimes you do have enough, there will be a numbering system for it. Okay, so over here, again, same idea. Again, what about this center right here? Well, number 4 is coming out towards you, so it's gonna be the reverse. Reverse, so we're down here, we're gonna go with the reverse dash and wedge. Okay, same priority, the same thinking on how to prioritize that doesn't change between these two molecules. So again, chlorine's gonna be number 1. 2 is gonna be this side over here, sort of to the right, because this carbon has a chlorine on it, and number 3 is gonna be over here. And again, we're gonna go 1, 2, 3. And again, it sort of looks like you're jumping over this hydrogen, but again, it's coming out and playing the board at your eye. So we're going, it's a reverse, we're going in a counterclockwise, so that's gonna be the R. Okay, same story over here, except number 4 is going away from you, so this is gonna be the standard, this will be the standard dash and wedge, okay? And again, we're going 1, 2, 3 in a clockwise manner, so that's gonna be the R. Alrighty? Okay, let me show you one. This is a reverse system. This is one that Wade had in the book. Okay, just, I don't know if you guys recognize this molecule, but thyroxine, controls metabolism. Okay, here's an example. If you look here, here's the chiral center, and none of the rest of this is chiral, by the way. It's just right here. And I don't know if you know, this is kind of interesting stuff. This iodine here, there's 2 of these, there's 2 forms, one's called T3, T4. T3 happens to be more potent than T4 as far as regulating metabolism. You make, I think you make T4 and that's released into your blood system, and then it's metabolized, your body takes off the iodines. I don't know, I always found this kind of interesting with this chemistry was, animals that hibernate, what they do, it's kind of crazy. You take all these iodines off, all right, so they take them all off, and then they decarboxylate out here, so they just have the amine and these 2 aromatics of one's a phenol. And that's how they keep their body temperature up, but shut down their metabolism. So if you ever decide you want to be a bear, you might want to see if you can get a hold of some of that stuff. But that's how, isn't that crazy? How the bears, that's what they slow down their metabolism, but to keep their temperature up so they don't freeze with that. I think it's called thyroxamine or something like that. Yeah.
So what is it that's generating heat?
That's out of my lane. I don't know exactly how they generate their heat. I suppose it's from metabolism in their cells, that they're, the energy from reactions that they do in their cells. Would it be, my guess is where they get their heat. Enough that their cells don't freeze. But having said that, my wife and I just watched this, what was it? It was on one of Discovery Channel or something about frogs, how they freeze. They literally burrow down and they freeze, but it doesn't kill off all their cells. And in the spring, when it warms up, they have pictures of these characters thawing out. I mean, their eyes look glazed over. It looks like you've had about 20 beers, and they're just all glazed over. And then the next thing, they have this photography, and it's showing, next thing their eyes are sort of moving, and it's like, wow, these guys are still alive. But they have some kind of protein that's in their blood system. It's almost like antifreeze, keeps it from disrupting the cells. Now we do the same thing in our lab. We use a glycerol solution when we freeze red blood cells at -80. We do that to them to keep them from going poof at -80. So I don't know exactly what they use. I think it's a protein. But anyway, that's away from this discussion. But there's chemistry everywhere, you guys. I just love it. Anyway, so let's go back and talk about, this is what we're supposed to be talking about. All right, so we're going to look at this chiral center here. Okay, hydrogen is going to be number 4. The highest priority would be the amino group. Okay, so now we're going to go down here. We're going to look at this carbon and this carbon over here. Now remember, this is essentially, carboxylic acid is essentially like having 3 oxygens attached to it. So, and this carbon here has 2 hydrogens, and then and another carbon over here. But those oxygens on here will give it a higher priority. Okay, so nitrogen's number 1, carboxyl's number 2, this carbon over here is 3. We're going in this direction, right? We're going in a clockwise direction, but look at this, it's the reverse system. So if you look up here, we're going to use this system here. It's going in a clockwise manner, so it's going to be the S. And the other one, again, this is essentially the mirror image over here of that. Again, if you prioritize the same way, number 4 is going to be the hydrogen, number 1 is the amine, carboxyl group is 2, and this carbon here is number 3. But again, if you sort of look at the steering wheel on this, you're going 1, 2, 3 in this direction, which is counter clockwise. So this is going to be the R R enantiomer. Okay. Anyway.
Is that really the mirror image? Like,
Yeah, this.
because the H and the
See,
N
these are nose to nose. These are both behind the plane.
Oh, okay.
And these are, even though this one's sort of away over here, these are both coming out of the plane of the board.
For the dash.
Well, yeah, the
Or
dash.
wedge.
The dash is going behind the plane. The wedge is coming out towards you. And all of this is sort of in one plane. It's kind of interesting too. Just one more tidbit. You know, you look at these molecules; they look flat, right? They're not. They're like this. They're like this, and it's because of the iodines. You got to have these two iodines to do this, to make those aromatic rings sort of almost perpendicular, or twist, each other. And if you don't do that, they don't work at the thyroxine receptor. Anyway, so long story. Here's another example. Okay, so the S enantiomer here. Okay, we're looking at this chiral center here. S is what you get with caraway seeds. You know, caraway you put into Italian sausage, rye bread, right? Okay, you guys cook, right?
I eat more than I cook.
You eat more, me too, but I do cook some things. I'm the grill master. Okay, and then R is the spearmint flavor, okay, and the chewing gum, all right? But let's go through and look at this molecule, and which one is it? Okay, here's the chiral center right here, okay? Now, what I did over here, and this, again, I put this in, this is right out of the book, is I went ahead and broke down these various functional groups. So here's the carbon-carbon double bond. That's why I've got these two carbons attached here. So the carbon here and the carbon here. Nothing you can do here. These are the hydrogens. Then I came up here, I attached a carbon here and a carbon here. On this carbon here, I put an oxygen, and this one out here, I put a carbon. Okay, that's what all of this is over here. So now it's time to go prioritize. So again, if we look here, we've got a carbon here, here, and here. Okay. So it's hard to make a call on that. You might have to dig a little further. So if you look here, you've got 3 hydrogens. Wait, we're at here. Okay, so we're looking at between these. So this has got 2 hydrogens. This has 3 carbons attached to it. Okay. So this group here, this vinyl methyl group, is going to take higher priority over these 2 groups here, these 2 CH2 groups, because this one has 2 hydrogens and this one has 2 hydrogens. So this vinyl methyl group will get the higher priority. So I'm going to give that number 1. Obviously, the hydrogen is going to be number 4. That 4 is kind of far away here, but that's for number hydrogen here. And then I have to make a decision on these 2 positions here. Okay, well, they both have hydrogens on them, 2 hydrogens, so you can't make a decision. So now you move further out, so you slide out a little further. Okay, so now we're going to be looking at this carbon here and this carbon here. This carbon has another carbon attached to it from the sort of breaking the system down. And then this one is going to have an oxygen attached here. And oxygen takes priority over carbon because atomic number of 8 versus 6. So this side here gets number 2, this side gets number 3. And again, if you look at the direction the numbers are going, again from 1, 2, 3, you're going in this direction, which is counterclockwise. Number 4 is going back behind the plane of the board. So we're going to use the standard dash and wedge on this one. So this one is going to be the S enantiomer. Okay, so I would highly recommend that you learn this, get this down right now, because You're gonna need it for, not only for these kind of problems, but for the Fisher projections, which we'll start talking about here pretty soon. Aha. Okay, so let's talk about Fisher. Okay, as I said at the beginning, where you see this is mainly with carbohydrates, and you also see it with amino acids. So you're gonna see this again. I'm pretty sure Dr. Z talks about this in biochemistry. Okay, so here's essentially the dash and wedge system. And so what I'm trying to show you is here, how do you put this into a Fisher type of drawing? And essentially what you're doing with this is you're taking this carbon and you're sort of pulling it down here. It's almost like you're squashing this thing down, flattening it out. And then you come over here, and again, what you do to determine whether this is the R or the S is you do a prioritization. But the Fisher system, and you know, there's a rationale behind why you go in the opposite direction on here, but I just can't remember what it is right now. But the Fisher system and the reverse, these two are the same, okay? So if you remember this, if you get this down, the Fisher system is the same. All right. Now, prioritization, same as the Kahn-Ingold pre-log. That doesn't change. So the prioritization part is not any different. But then you have to go in and prioritize these. So again, we've got an oxygen versus a hydrogen versus carbon versus another carbon. So obviously oxygen at 8 takes priority over hydrogen and carbon. So this will be number 1, hydrogen's going to be number 4. Okay, then we've got to make a decision between this carbon and this carbon here. This one has essentially, if you break it down, it's going to have essentially 3 oxygens attached to it versus none down here. You've got 3 hydrogens. So this carbon up here will take priority over this lower carbon. The other thing, just mention this now, when you draw these Fisher projections, we're going to draw some, so probably not Monday, Wednesday, we're going to go over a bunch of these problems. So, but you always try to draw with a carboxylic acid. It's the highest oxidation state over here of the carbons attached. You always try to draw that at the top. For some reason, there's a system that they use in this that you always put the highest oxidation state at the top. So what's sort of the rule on that? It's carboxylic acids are number 1, number 2 are aldehydes, and number 3 would be a CH2OH, okay?